In this section, we're going to learn about Euler paths and Euler circuits. First, let's talk about an Euler path. An Euler path is one that travels through every edge of a graph once and only once. Okay, you don't retrace your steps. Each edge must be traveled and no one can be retraced. So on this one, let's look at this path they have created here. They did A to B, and then B to E was 2. Then they did E to F third, F to D, D to B, B to C, C to E, E to D, and D to G. Since we traveled every edge once, and we could trace the whole thing with our pencil without picking it up, that is considered an Euler path. Now let's look at a circuit. An Euler circuit does the same thing, except it begins and ends at the same vertex. Okay, so in this case, they have an Euler circuit starting here. So we're going to begin and end at A. It goes from A to B, B to E, E to F, F to D, D to B, B to C, C to E, E to D, D to G, and G to A. Because it began and start with A, that is considered an Euler circuit because it only touched each edge of the graph once and only once. Now, this is Euler's theorem. And Euler's theorem, what it does is it explains when you'll have a path or a circuit. Okay? So these following statements are true for connected graphs. Remember, they have to be connected, okay? If a graph has exactly 2 odd vertices, then it has at least one Euler path, at least one, but no Euler circuit, okay? Each Euler path must start and end at one of the odd vertices. So it must start and end at one of the odd vertices, okay? Has to start at one of them and end at the other one. All right, let's look at the next one. If a graph has no odd vertices, they're all even, okay? It has at least one Euler circuit, okay? Which is also an Euler path. It's a path that begins and ends at the same vertex, okay? It can start at any of those vertexes, so keep that in mind. And lastly, if a graph has more than one, or excuse me, more than 2 odd vertices, then it has no path and then no Euler circuit. Okay, no Euler path, no Euler circuit. All right, it says explain why the graph of this figure has at least, let's see, sorry, messed up a little bit. My picture's in the way. We can fix that a little bit. Okay, it says that explain why the graph of the figure has at least one Euler path. Use trial and error to find such a path. So first we want to look at the vertexes. Okay? We need to look at these and see what the degrees are. This has a degree of 2. Oops, they have them listed down here. This one is 2. C has a degree of 4. B has a degree of 4. It means that's 4 edges coming out of it. D has 3. And E has 3. So this one has 2 odd vertices. This one is going to have an Euler path, but not an Euler circuit. On this one, we want to find one of those paths. Okay, now that we know it has one, let's find it. You need to start at one of the odd vertices. We either want to start at D or E. They chose to start at D. Okay, so they went from D to C, C to B, they put a 2 there, B to E, they put a 3 there, E to C is 4, C to A is 5, A to B is 6, B to D is 7, and lastly is D to E, and that would be the 8th. Remember, it has at least one, there could be more, but they have to start and end at the odd vertice. Right, so this one is an application of the Euler theorem. It says we can use it to solve the Koenigsberg, I always saying that incorrect, but the Konigsberg problem, okay? What we can find, and move the picture down here, when we look at these vertices, this one has a degree of 5, this one is 3, this one is 3, this one is 3. They are not going to have an Euler path, okay, because we have to have exactly 2. And they're also not going to have a circuit because for a circuit they all have to be even. So what we know by using Euler's theorem is that it is not going to be possible for us to find a path through these.